Imagine a future battlefield scenario, not in decades, but in the immediate future.
Powered by a 100 kilowatt-hour battery array, it possesses enough energy for 6 minutes of continuous firing.
If connected to a generator driven by the truck's own 500 horsepower engine, this battery can be fully recharged in approximately 16 minutes.
An air defense radar detects a squad of 4 low-flying jet aircraft.
This tracking data is relayed to the laser weapon.
Normally, the pilots would have a 40 to 60 second window from the moment of radar detection to release their payloads and evade.
However, this new weapon operates at the speed of light.
The laser focuses its 1 megawatt beam, originating from a 1 meter wide turret,
into a 5 centimeter wide spot at a distance of 50 kilometers.
At this range, the beam's intensity reaches a staggering 50 kilowatts per square centimeter.
The first aircraft is transformed into a fireball within 200 milliseconds of the beam's impact.
The entire hostile engagement involving all 4 aircraft is neutralized in less than 4 seconds.
Evacuated someone's dead.
Our Bros is fiction. This is not science fiction.
This technology, albeit at lower power levels, is already being deployed in live war zones, heralding a fundamental shift in military strategy. This analysis will investigate the impending era of laser weapons.
Exploring their mechanics, the challenges their deployment, and the transformative impact they will have on modern warfare. The aggressive pursuit of DEW technology by global militaries, marked by millions in annual R&D spending,
stems from a compelling strategic rationale.
The lasers familiar to the public, handheld pointers or entertainment displays, are orders of magnitude weaker than even a standard light bulb.
Military-grade lasers for range finding or target designation are only marginally more powerful.
A laser weapon, however, has a different objective: catastrophic structural failure.
It achieves this by focusing tens of thousands of watts onto a minuscule point, inducing thermal shock equivalent to a dozen blowtorches, melting metals and detonating fuel stores.
Today's most powerful deployed systems, such as Lockheed Martin's, wield 300 kilowatts.
capable of delivering energy equivalent to a stick of TNT to a target every 3 seconds.
Military planners, however, envision the 1 megawatt green wavelength laser as the true objective.
With such a system, fleets of drones would be destroyed as fast as the turret could switch targets. Waves of over 100 missiles could be eliminated without the need to reload.
Even low-orbit satellites would be vulnerable, their solar panels melted or their sensitive optics permanently burned. However, lasers are not an ultimate weapon.
They remain dependent on external tracking data, restricted to line-of-sight engagements, and present an enormous electrical consumption challenge. Properly armored vehicles, like main battle tanks, can still shrug off their beams, and they are useless against targets beyond the horizon. Yet, the advantages they offer, light speed engagement, deep magazines, and a low cost per shot, are too profound to ignore.
The conceptual framework for laser weaponry is not novel, tracing its lineage back over 60 years. By pumping energy into the crystal, chromium atoms were excited and shed photons.
Encased in a mirrored tube, these photons cascaded, emerging as a synchronized laser beam.
This first laser, however, was incredibly inefficient, akin to igniting a bonfire to get a candle's worth of light.
The intervening decades saw a rapid exploration of pump sources, many of which proved to be technological dead ends. Engineers investigated fluorescent dyes, high explosives, and even radiation from nuclear reactors. The most prominent effort was the YAL-1 airborne laser. A Boeing 747 carrying system generated a megawatt beam from a 1.5-meter mirror by mixing toxic, explosive chemicals. While it proved a megawatt-class weapon could fly, it was grotesquely impractical.
Carrying fuel for only 20 shots at a program cost of $11 billion.
Similarly, a Soviet attempt to orbit a 1-megawatt carbon dioxide laser failed when its rocket crashed.
These early systems were too complex, dangerous, and inefficient for battlefield use, stalling the laser's promise for decades.
The requisite breakthrough emerged not from exotic fuels, but from the solid-state revolution: fiber lasers and semiconductor lasers.
These technologies provided a path to high-power systems that were efficient, robust, and scalable. A fiber laser operates by sending light from a source down a specialized optical fiber doped with elements like ytterbium.
The extended length of the fiber allows these atoms ample opportunity to absorb the pump energy
And release it as a narrow, high-quality laser beam.
Semiconductor lasers, conversely, function like solar cells in reverse.
They consume electricity to release photons from materials like gallium arsenide, using microscopic mirror layers to...
The true key to unlocking weapon-grade power, however, is beam combining.
A single fiber or semiconductor laser module might only produce 100 to 1,000 watts before succumbing to internal heat.
Beam combining is the technique of merging dozens or even hundreds of these individual high-quality beams
into a single, massive, and coherent beam.
This modular approach is what enables modern systems to climb into the hundreds of kilowatts.
With electrical to light efficiencies now reaching 30 to 50%, these systems are compact, reliable, and
making them viable for integration onto trucks, ships, and aircraft.
Achieving high power is only half the battle. This power must be delivered effectively to a target kilometers away.
The first challenge is the physics of destruction.
The effectiveness of a laser is measured by its intensity on the target.
A drone may require approximately 1 kilojoule per square centimeter to destroy.
A missile or aircraft, however, requires tens of kilojoules per square centimeter, and an ICBM warhead's heat shield demands hundreds.
A 10-kilowatt laser, for example, would take nearly 8 seconds to defeat a simple drone, a dangerously long time in combat.
This illustrates why power thresholds are so critical.
10 kilowatts for drones, 100 kilowatts for missiles at short range, and climbing to a megawatt for fighter jets and hardened targets.
The second major challenge is the atmosphere itself.
A laser beam does not travel through a vacuum.
It is scattered by dust and clouds.
Key wavelengths are absorbed by atmospheric gases. Water vapor, for example, completely blocks the mid-infrared beams of carbon dioxide lasers.
Most problematic is atmospheric turbulence, the same phenomenon that makes stars twinkle.
Which acts as a moving lens, distorting and bending the beam, blurring its focus and dissipating its intensity.
To counter this, engineers use adaptive optics, flexible mirrors that deform hundreds of times per second to undo the distortion in real time. For fog or dust, the only solution may be brute force, using the laser's own power to vaporize a channel through the air.
The final barrier to laser weapon adoption, cost, is now collapsing.
The YAL-1 program cost $11 billion for a single, impractical prototype.
A 2024 U.S. Naval Institute report estimated a 250 kilowatt system at $200 million.
By the end of this decade, a 1 megawatt laser may cost no more than a main battle tank, enabling widespread proliferation.
This will fundamentally transform warfare.
As an air defense weapon, a 1 megawatt laser is an inexhaustible counter to drones and missiles.
Forcing adversaries to attack in low-altitude, fuel-inefficient profiles.
This severely curtails the effectiveness of air dominance, a strategy upon which Western militaries have relied for decades.
Akin, the strategic implications are profound.
A ground-based laser could destroy a satellite in a 400-kilometer orbit in just 4 seconds.
Potentially clearing entire orbital bands of intelligence assets.
At sea, lasers will serve as an inexhaustible defense, forcing navies to reconcentrate into large fleets.
To overwhelm a target with a single, massive volley. For nuclear strategy, affordable laser systems make ballistic missile defense plausible for smaller nations.
Paradoxically, ground forces, like tanks, become more valuable as the aerial threat diminishes.
The era of laser weapons is no longer a theoretical exercise.